Hello and welcome to this lecture series on microprocessor and microcontroller. And we are in 11th video of this particular lecture series and we are trying to study 8086 microprocessor starting from this video onwards. So on 8086 microprocessor, this is our first video and we have completed 8085 microprocessor prior to that. So the topic of today is going to be the architecture of this 8086 microprocessor. Now, since we have already learned how 8085 microprocessor works, we have already seen its architecture, pin diagram, then the interrupt structure, external memory structure, and how things happen within 8085 microprocessor. So obviously, when we will study 8086 microprocessor, there will be a frequent comparison between 8086 and 8085 microprocessor, right? And 8086 being a microprocessor which came after 8085, so it is also very obvious that it will be an advanced version. And the important thing about 8086 microprocessor is that it is a blueprint to all the processors that came after it. Means after 8086 microprocessor, there were many microprocessors that this Intel family has produced, but the popular among them were Pentium microprocessors. Then there was this dual core to duo series, and there were these i3, i5, i7, i9, etc. So the good thing about studying 8086 microprocessor is if you study this microprocessor, you have also studied all of them to certain extent, right? So they maintain backward compatibility, and it all started from 8086, not from 8085. It is again a backward compatible in some sense, but 8086 can be thought of as a very good blueprint of all the successors of this Intel family series, right? So let me begin this 8086 discussion by just showing you what we have done up till now and what we are going to do. So up till now, we have covered 10 lectures. We have covered 10 lectures, and in these 10 lectures, we have discussed 8085 microprocessor. So we covered the digital hardware, logic, history, and then difference between microprocessor and microcontroller in the first lecture, which was a generic lecture where we discussed what microprocessor and microcontroller is. Then we saw the programming model of 8085, that is the portion of this microprocessor which is accessible to the user for interacting with it in the sense of programming. There we also saw the meaning of programming. Programming simply means that out of the 74 instructions which were available in 8085, 246 patterns could be made, and a permutation and combination, a logical permutation and combination of those 246 patterns is called as a program. So we studied how to make some basic programs in that. We then saw the architecture, pin diagram, and then the interrupt structure. Then we saw machine cycles and timing diagrams, input output, and addressing modes and instruction set of 8085. So in the laboratory courses, in the laboratories, we have seen a lot of programs about 8085, etc. So on the same lines, this is the tentative, these are the tentative titles in which we will be reading 8086 microprocessor. So I will probably begin with architecture of 8086, which is the topic of today. And in this lecture, we will also cover the points of differences between 8085 and 8086. Although a mention of these points of differences will be in the subsequent lectures also, but we will try to have a good comparison between the two microprocessors in this lecture. We will then see the pin diagram, then the programming model. We will make some simple programs, and then we will see the minimum and maximum mode of 8086. This is something which is absent in 8085 microprocessors. So we will first of all discuss what these modes are and what are the advantages of these two modes, right? So just to give you a brief idea, 8086 is again an integrated circuit. So that integrated circuit can be used in two modes. One mode is where there is only one microprocessor and it is controlling all the other peripherals. So there is only one control center, one microprocessor that is just doing every task in the circuit. So that's what we mean by minimum mode of 8086. And maximum mode means there is a network of various microprocessors, not 8086 only. There can be 8086, 8085, Pentium. Then there can be microprocessor from other families like AMD, Qualcomm. So there are these multiple microprocessors which are connected in a network, and they are trying to interact with each other. So that's what we mean by maximum mode. So this IC of 8086, it operates in these two particular ways: minimum mode and maximum mode. Then we will see instruction template and memory organization plus some miscellaneous topics of 8086. Then we will study, of course, the addressing modes, instruction set, and we will dedicate some time for programming. So this is a tentative list of topics that we are going to cover in depth, and I might just change them or shuffle their order of appearance depending upon the need of the course. So that's what we are going to do here, right? So now let me just begin this topic by showing you the actual uh, architecture of this 8086 microprocessor. Right. So this is the architecture of 8086 microprocessor, and let us first have a look at this architecture, and let us see if we are seeing some familiar components here in comparison to 8085, right? So although we do not know anything about this as of now, but let us see if we can just figure out some components which look similar to 8085. So here you can see that the arithmetic logical unit is of 16 bits. There in 8085, we had a 8-bit arithmetic logic unit. And on that note, it was called as a 8-bit microprocessor. So the first point is that 8086 microprocessor is a 16-bit microprocessor, right? So this is arithmetic logic unit. Then we also see flags here. Flags are also of 16 bits here. Earlier in 8085 microprocessor, they were of 8 bits, right? Out of which 3 were don't care conditions, and we had carry, parity, auxiliary carry, then sign, and 0. Sorry. So flag registers are also little bit familiar to us. Then there is timing and control circuit, which was also there in 8085 microprocessor. Then we have a decoding circuit, which we have also seen there. We have this stack of registers. So, sorry, if we talk about 8085 microprocessor, we had A, B, C, D, E, H, L, and M registers. Here you see that the nomenclature has changed. You have AX, BX, CX, DX registers, and they are divided into these two parts: AH, AL, BH, BL, CH, CL, and DH, DL. So what are these? So if you think about this AH register, this is the higher order byte of this AX register. AX register is a complete 16-bit register, and it is divided into two parts: AH and AL, A higher and A lower. So AL is the lower byte of AX register, and AH is the higher byte of A register. So you can use these registers either in 16-bit mode. I mean, if you can use AX completely, which will be a 16-bit register, or you can break them in parts. You can use that as AH register or AL register. So this facility was not available in 8085. There was only ABCD HL registers, and at one time you can use one register completely. Half register cannot be used there, or even if you have to use it, you have to write specific programs for that. So direct commands were not available in the instruction set, but here in the instruction set we will see that there are commands where AL, AH, and AX can be used as three separate entities, right? Similarly, BX, CX, and DX registers, they are also bifurcated into two parts. They all are of 16-bit, and half registers can also be used. Now, like in the case of 8085 microprocessor, we called A register as the accumulator. So here also AX register is called as the accumulator register. Now, like in 8085, A register was responsible for default calculations, and it was also present in some default command. The same will apply here also, but the involvement of this particular register now in default calculation is less as compared to 8085. I mean, in 8085, if you see the subtraction command, one operand was fixed to be A register, and other could be anything else. It could be data or another 8-bit register. However, in this subtraction command will have two parts on which it will operate, and none of them will be by default considered as AX. So that is also one point of difference. But still, we call this as accumulator register. It is of 16 bits, and this is the primary reason why this 8086 microprocessor is a 16-bit microprocessor. Right. Now, so apart from these registers, we have got stack pointer, we have got base pointer, source index, and destination index. So SP stands for stack pointer. This was also there in 8085 microprocessor. And here, this register is completely of 16 bits. Similarly, base pointer, source index, and destination index, they are also of 16 bits. Now, they have got some very specific purposes, which we will study when we will come to the details of these registers. But at this point, all I can say is you should have this general information that C register is usually used as counter. It is by default used as counter with some very specific commands. And we will see that when we will do programming, that C register is by default used as counter register. Right. Similarly, A is the accumulator, and then these registers also have special purpose: source index, destination index. So when the time will come, we will come to know what are their special purposes. So this is a register stack, which is also something which is familiar, which looks familiar. Then now, if you see the upper portion of this particular circuit, now you can see that there are other registers also: CS, DS, ES, SS, and IP. So now this is called as code segment, data segment, extra segment, stack segment, and then instruction pointer. So this instruction pointer is similar to program counter in 8085. So it will hold the uh, address of next instruction to be executed. But the statement that I have just made is not completely true. It is partially true. It will hold the instruction. It will hold the address of next instruction to be executed, but that is not the complete address, because in this 8086 microprocessor, there is addressing mechanism is little bit different as compared to addressing mechanism of 8085, because the externally interfaced memory that we connect to this particular microprocessor, it is segmented. I mean, in 8085 microprocessor, you just had one memory. That one memory was having a size of 64 kilobytes, and inside that you could put your data somewhere, you could put your code somewhere, and you could begin any operation from anywhere, right? So there might be a situation where suppose you have kept your data somewhere, and prior to that location you have started writing your program. Some locations before that data you have started writing your program, but what happens is your program becomes so long that it overwrites the data. So to avoid that, in 8086 we have segmented memory. There is a separate section for code, there is a separate section for data, there is a separate section for extra activities, and there is a separate section for stack. So in the externally interfaced memory, it has got these four different sections, and these four different sections, their addresses are kept in this code segment, data segment, extra segment, and stack segment. The names are similar. These are the pointer registers that you have got here. These will be pointing to the necessary locations in the external memory. So you will have code segment, data segment, extra segment, and stack segment in the external memory, and their base addresses will be kept in CS, DS, ES, and SS register. Right. So these are called as segment registers, not the pointer registers. Sorry, these are called as segment registers. So segment registers are internal to microprocessor, but the segments, they are actually externally placed inside the external interfaced memory of microprocessor. Right. So one more information: the externally interfaced memory in this case is your 1 megabyte, 1 MB. How is that possible? Because this microprocessor is a 16-bit microprocessor. So the data bus automatically has to be of 16 bits, right? Since this microprocessor is a 16-bit microprocessor, so the internal data bus has to be of 16 bits. And the address bus of this microprocessor is of 20 bits. The address bus of this microprocessor, as you see here, it starts from AD0 to AD15, and then A16 to A19. I mean, in totality, it starts from 0 index to 19 index, which means that it has a total of 20 bits. So the address bus is of 20 bits. and 2 raised to the power of 20 is nothing but 1 megabyte. So to this particular microprocessor, you can always connect a externally interfaced memory, which has got a maximum of 2 raised to the power of 20, that means 1 megabyte locations. And inside that memory, you have got various segments. So those segments are code segment, data segment, extra segment, and stack segment. And to keep the base address of those four different sections inside this microprocessor, you have got this segment registers, right? So that is the relevance of these segment registers. So this also makes it very clear that this microprocessor, since it is 16-bit microprocessor, data bus is of 16 bits and the address bus is of 20 bits, right? Let us see then again some more components which look familiar. Now, this is a adder, address conversion mechanism adder. So this was not present in 8085. Now, what is the purpose of this? An important point to note here is that the CS, DS, ES, and SS, these segment registers are also of 16 bits each. Similarly, instruction pointer is also of 16 bit. So, uh, and we said that the externally interfaced memory will have at max 2 raised to the power of 20 locations in it, right? So it can address 1 megabyte of memory, and each location will be of 1 byte again. It's not that one memory location will consume 16 bytes. At every memory location, you sorry, you still have a 8-bit storage capacity. So you have 2 raised to the power of 20 locations. Each location has got a 8-bit capacity. This is 1 byte capacity. So now if you see, the address of every location could be of 20 bits. Its address has to be of 20 bits. But these registers you see, code segment, data segment, extra segment, stack segment, they are of 16 bits. And I told you that in the externally interfaced memory, the base address, not the actual physical address, the base address is kept in code segment, data segment, extra segment, and stack segment. So what is this base address? This base address has to be of 16 bits only. And what is this base address and how is it converted to the actual 20-bit physical address? We will come to know when we will study the relevant topic, right? So these are of 16-bit registers, but do not get confused. The externally interfaced memory uh, can be addressed by 20 bits only, but still the base addresses, there is something called as base address which is kept in these registers. So base address plus something else will make the actual physical address. We will see how that conversion is done, and that conversion is done through this particular adder. So this is adder conversion mechanism, address conversion mechanism. So this entire thing is done here. Although there is an adder in this ALU in itself for performing mathematical calculations, but just for address part, you have this separate adder here, right? Then there is a new thing that we see here, which is called as this instruction byte queue, which is of 6 bytes, right? So now this instruction queue was not there in 8085 of 6 bytes. It was not there. There was just one instruction register from where what we were doing is from the externally interfaced memory, we read the code byte by byte and then it gets processed. Once one byte gets processed, the next byte is entered and it gets processed and so on. But here what happens is while this ALU is processing something, this instruction queue is loaded with 6 bytes from the externally interfaced memory, right? So suppose if 2 bytes are consumed in this particular thing, so it will again take 2 bytes from the externally interfaced memory and keep them here, so that the execution part is separated from this fetching part, fetching of instruction part. If you're fetching instructions from the external memory inside the microprocessor, and then concurrently executing it. So what will happen is you fetch one instruction, execute it, then when it gets completed, you fetch the next instruction. This was what was happening in 8085. But here, once you fetch this complete queue, you start executing some instructions from some bytes from here, and this queue never gets empty, right? It keeps on fetching the instructions so that this fetching part does not interferes with the execution part. So these two units of the microprocessor, the upper unit and the lower unit, they operate independent of each other. I mean, it does not matter. This lower unit, it is called as execution unit, and the upper unit is called as the bus interface unit. because most of the things that you will see on the upper side, they correspond to either address generation or taking the data from external memory into the instruction queue and so on. So the functioning of this bus interface unit is independent of this execution unit. In execution unit, actual control signals are generated by using this timing and control circuit. Arithmetic logic unit performs its calculation and so on. So this execution unit should not wait for the fact that it is executing one instruction, then when it will complete, then only it will instruct the external memory to fetch one more byte. So it does not perform this way in 8086. In 8086, this instruction queue of 6 bytes is there, and uh, this queue usually remains full. And once 2 bytes of this are empty. Suppose 1 and 2 instructions are used, so this 6534 will shift downwards and two locations from here will become empty. And then the fetching part will start in concurrently with this particular execution unit. So this unit has never to wait for fetching of instructions. It is already available in this instruction queue. And why is the size of this 6 bytes? The size of this is 6 bytes because uh, instruction which can take maximum number of bytes in 8086 is of 6 bytes. So it is call instruction, and we will see it when we will come to the appropriate programming part, maybe in the lectures or laboratory. So this phenomena is called as pipelining. I mean, you are keeping the working of bus interface unit, or BIU for short, and execution unit, or EU for short, independent of each other. So this phenomena is called as pipelining, and pipelining is also responsible for faster speed of 8086. Although the clock that this microprocessor uses is of 5 megahertz, right? Its frequency is 5 megahertz, but it has got its variants also, which will be using 8 megahertz frequency and 12 megahertz frequency. But the version that we are studying will use 5 megahertz frequency. That is the primary version, and that 5 megahertz frequency is obviously higher than the 3 megahertz frequency that 8085 was using. So obviously this microprocessor is faster. But then the second fact that adds to its speed is it has independence in operations of execution unit and the bus interface unit, so that whenever these they perform their operation, execution unit does not depend on this bus interface unit for waiting for instructions. They are always available in this instruction byte queue, right? So rest portions, as you see, are familiar to you. This is the internal data bus. This is C bus. This is A bus. If it is A bus, it is meant for the execution unit. C bus is meant for this particular bus interface unit. You can see that it is also written here: bus interface unit and execution unit, right? So then you have this memory address and data bus interface. Obviously, there will be some pins, and here also this address and data pins are multiplexed with each other. So we will see when we will study the appropriate pin diagram, when how these are interfaced, how these are multiplexed with each other, and what latching mechanism like 8085 is used here, right? So this is more or less the internal architecture of 8086 microprocessor, and now we will discuss this in little more detail. We will see the structure of these flag registers, as well as we will see the structure of the external memory and the clock, the kind of clock that is required, right? So let me just first show you the structure of memory. So here what happens is, we already know that it has got 2 raised to the power of 20 possible addresses, because the address bus of this 8086 microprocessor is of 20 bits. So it can address a maximum of 2 raised to the power of 20 address locations, right? So that 2 raised to the power of 20, when translated into mega terminology, it will become megabyte. 1 megabyte. 1 mega locations are there, and each location is of 1 byte. That is why it is called as 1 megabyte. So here you will find 2 raised to the power of 20 locations. Now, as discussed earlier, this complete memory is divided into 4 different segments: code segment CS, data segment DS, extra segment ES, and stat segment SS. And each of this segment is of 64 kilobyte, that is 2 raised to the power of 16 bytes. This is also 2 raised to the power of 16 bytes. This is also 2 raised to the power of 16 bytes, and so on. So 64 kilobytes, if you sum it for 4 times, you will just get 256 kilobytes. Now, four segments, they consume 256 kilobytes, and the total memory is of 1 megabyte. So, three-fourth of the memory still remains. Three-fourth of the memory still remains if you have made these four segments. Although it appears that these four segments are completely covering this entire memory, but this is not a diagram which is true to scale. So if you see the 64 and 64 kilobyte, these are four sections. So the complete memory that these sections occupy is 256 kilobytes. And the since the complete memory in 8086 is 1 megabyte, so still three-fourth of the memory remains apart from these segments that you see here. So what do we do with that remaining memory? So in that remaining memory, some programs which are used to start that microprocessor are written. So in modern terminology, we call it as an operating system. Whenever you install any operating system into your computer, if you talk about Windows operating system, then in C drive, some of the space is taken. So similarly, in this microprocessor, in the remaining portion, we write some programs which are used to start this microprocessor and which have got some interesting subroutines of what should happen when an interrupt occurs, or some interesting subroutines are written there, right? So now, is it necessary that whenever we have this external memory of 1 megabyte, we should have all of these four segments in our program? No, it is not necessary. For example, your program might require code segment only. You don't have huge data to keep, so you won't be using data segment. You don't have extra tasks in your program, so you won't be using extra segment, you won't be using stack segment. So it might be possible that some of the programs might only require code segment, so you will be just designing this code segment inside memory. It's not fixed that code segment will start from this particular memory location and end at that particular memory location. That is left to the programmer. I mean, you can choose to start your code segment from anywhere in the memory and it will consume 64 kilobytes. Although the choice given to you is arbitrary, but there is certain restriction on the starting address of that. The starting address, if you see the actual physical address of every memory location, is it is of 20 bits. So if you see it in hexadecimal representation, it will consume 5 hexadecimal digits, right? So it will contain 5 hexadecimal digits. So out of that, it is mandatory that the starting of any of these segments that you see here, the last hexadecimal digit should always be zero. I mean, if you see the hexadecimal representation of the actual 20-bit physical address, it will be of 5 hexadecimal digits. And it is mandatory for the starting section of code segment, data segment, extra segment, or stack segment to have that least significant hexadecimal digit as zero. Or alternatively, you can say that if you are seeing it in binary, if you are seeing the 20-bit physical address in binary, then the last four bits or the least significant four bits have to be zero. So that is a condition for the starting address of this code, data, extra, and stack segment. And we will come to know why this condition is there. And from that particular location, you can start your code segment, data segment, extra segment, and stack segment. So it is not necessary that all of these should be there in your program. You might use one or two or a combination. Now, is it possible that you can have two data segments in your program? Yes, it is also possible. So, I mean, in your program, you can have one code segment and you might initialize two data segments. You might initialize two data segments somewhere, because ultimately you have got a huge memory which is 1 megabyte, and three-fourth portion is still remaining. So in that three-fourth portion, not complete three-fourth portion is used for writing the operating system, although operating system is a new terminology. It was not used at that particular time. So instructions which are used for keeping this microprocessor working are written in that remaining three-fourth memory, but that three-fourth memory is not used completely by those instructions. That is still vacant. Most of the memory is vacant. So you can define two data segment or might be two extra segment in your externally interfaced memory through programming, depending upon your need. And we will do it when we will come to the programming part. So This is a very elegant way of actually keeping your code section, data segment, extra segment, and stack segment separately. Now, this extra segment can be used for any general purpose. You can implement, you can keep some data into it, you can keep code into it, you can also write some stack into it, right? So that is also there. So this is a general introduction to the externally interfaced memory of 8086, which is 1 megabyte in its complete extent. So now let us also come to the structure of flag register. Now, let me just show you first of all the architecture again. uh, Here you have got these flag registers. So these flag registers are of 16 bits. In 8085, they were of 8 bits. Now let us see how the flag register looks like in 8086 microprocessor. So here you see, if you see the least significant 8 bits, so they are same. They are same and they are exactly same as 8085. Carry, parity, auxiliary carry, 0, and then sign. Right? So this portion is exactly same as 8085. So this maintains the downward and upward compatibilities. The programs which will work in 8085 might also work in 8086 if you use appropriate commands, because there is no change of this flag structure as you can see here, right? So this sort of maintains upward and backward compatibility here. And these three don't cares are also placed at the exact same locations as it was in 8085. Now let's talk about the bits after sign, because we already know what is the meaning of carry, parity, auxiliary carry, and then 0 and then sign flag, right? So in case you have forgotten them, you can see the appropriate lecture in 085 and get the meaning of these. Now there are some extra flags, which is called as trap flag, interrupt flag, direction flag, and overflow flag. So trap, why is trap used? So in programming, what happens is usually when you are typing your program onto an editor, you would like to debug it line by line. So that facility is inbuilt into this microprocessor 8086, and for that you have this trap flag. So if you just make the value of this trap flag as 1, then what will happen is you will be able to execute your program line by line or instruction by instruction, right? So that is used for that particular purpose. Then you have got interrupt flag. So this interrupt flag, it is used in the same way as we had that interrupt flag in 8085, but it was not a part of this status register. However, this has been included as a part of this status register here. And then you have direction flag. This direction flag, it since in 8086 instruction set, there are certain instructions which will deal with string operations. By string operations, we mean like in C programming language, you all must have been printing hello world onto the screen or taking a string from the user as input. So for those string instructions, if the string is kept in externally interfaced memory of 8086, so do you have to read the string in forward order? That means in the increasing order of addresses, or in the reverse order, that is in the decreasing order of the addresses. So in whichever direction you keep your string, that can be set by this direction flag. If the value of this D bit is 0, in that case, with the increasing addresses, you will keep your string. And if this flag becomes 1, then in that case, you will be keeping the string in reverse order of memory. Means now you will be keeping the addresses from higher address to the lower address. So that is used for that particular purpose, direction flag. And this overflow flag is used when there is an overflow in your calculation, right? So these flags are also available to the programmer through various commands, right? Like in 885, we have also seen that we can tamper with these values by taking the flag register into your accumulator and then actually changing it and then actually putting it again into the flag registers. So that kind of thing can also be done here. But additionally, these flags, that is trap, interrupt, direction, and overflow flag, they appear in the instruction set in various commands to set or reset them. And then these 4 bits are kept as don't care conditions. So they do not have any usage. They are reserved for future microprocessors. So if you study any microprocessor that is after that, it is probable that these 4 bits will also be used for some purposes. So this is the structure of complete 16-bit flag that we have in microprocessor 8086. Now, let us talk about the structure of the clock that we have in 8086 microprocessor. So, obviously, you have to use a pulse in clock circuit, and the kind of pulse that we are using in this 8086 microprocessor is very specific. It has to be a pulse which is on for 33% of times, and for rest of the times it is off. That means alternatively we can say that we need a pulse that's whose duty cycle is 33%, whose duty cycle is 33%. All of you might be aware of this terminology. Duty cycle simply means that in one period of this periodic pulse, the time for which that pulse remains on, or the T on of this pulse is 33% of the times of the entire period. So that's what we mean by duty cycle. And for 8085, we use a pulse which has a 33% duty cycle, and the frequency of that to begin with is 5 megahertz. So the basic variant of 8085 will be using a frequency of 5 megahertz, right? So we have three versions for 8086. One is 8086, another is 80861, another is 80862. So 8086 uses 5 megahertz, 80861 uses 10 megahertz, 80862 uses 8 megahertz frequency, right? So 5 megahertz, 10 megahertz, and 8 megahertz. Like in today's time, we have if we talk about Intel's i5 processor, so i5 comes in various generations, right? So we similarly have an older terminology where we have 8086, which operates on 5 megahertz, 80861, which operates on 10 megahertz, and 80862, which operates on 8 megahertz. But in this course, we will restrict ourselves to the base variant, which is called as 8086 and which operates on 5 megahertz. And the specialty of the pulse that we need for operating this is it has to has a 33% duty cycle. So to be able to generate this pulse through a crystal oscillator, we have a specific IC for that, and we will see the structure of that IC when we will study that clock completely in details, right? So this kind of thing is needed there. Now, let us again just rewind the definition of microprocessor. We have already seen this definition. The microprocessor is the brain of a computer. It is multi-purpose, clock-driven, register-based, programmable, integrated circuit, which takes binary input, processes the binary input according to instructions already stored inside it, and then produces binary output. So we are also already aware of this definition of microprocessor. So this definition is just there for revision. And let me now just point out some important points that we have discussed up till now, or maybe some of the points would have been skipped. So they are summarized here for this particular lecture. So this 8086 microprocessor is a 16-bit microprocessor because the data bus of this microprocessor is of 16 bits, right? So address bus is obviously of 20 bits, which we will discuss later. So now four 16-bit general purpose registers are available: AX, BX, CX, and DX. This is also what we have seen. Then we have got eight 8-bit general purpose registers. That is A lower, A higher, B lower, B higher, C lower, C higher, D lower, and D higher. So this is not I, this is actually L. I have written it in small. It should have been capital L. So A lower, A higher, and similarly there are variants for every register. And you can use any combination. It's not necessary that if you are using DX register, then you have to use C also in 16-bit mode. So you have to use CX register. No, it is not that. You can use DX register. You can use CH register in some program, and it is also possible that you are using DX register and you are also treating this DL and DH independently. So any combination of these registers can be used according to your need. So since the registers are given in 16 and 8-bit modes, so you will be able to write programs for 8-bit and 16-bit operations both. So obviously the instruction set will be such that there will be some 16-bit operations mainly, and some operations are also there for 8-bit calculations. One good thing about 8086 is that unlike 8085 microprocessor, you will notice that in the instruction set there are commands for multiplication and division as well. However, in 8085 these commands were absent. So the instruction set of 8086 microprocessor is richer as compared to 8085. 85 microprocessor. In 8085 microprocessor, we had 74 instructions. However, in this 8086 microprocessor, we will have near about 117 instructions. And if you talk about combinations, many combinations of that can be made. In 8085, we only had 74 instructions, whose 246 combinations were there, right? So here we have 117 instructions near about, and we can make many combinations of those instructions, right? So this is also one point of difference, that is the instruction set of 8086 is much richer as compared to 8085, because there are direct commands for multiplication, division, and you will see a lot of other operations will be very easy. They can be done by a single line command. Earlier in 8085 we had to write separate programs for that, so that is not the case here. Then the externally interfaced memory is of 1 megabyte, which we already know because the address bus is of 20 bit. So 20-bit address bus will be able to address 2 raised to the power of 20, that is 1 megabyte. 1 mega stands for total number of locations that will be there in memory, and byte stands for the fact that every location is of 1 byte, that means 8 bits. So we have 1 megabyte storage, which is external storage, and this external storage is divided into four sections: extra segment, code segment, then you have data segment, and then you have stack segment, right? So these all segments are there. Apart from there, three-fourths memory remains, in which there are some special programs which are written to keep the microprocessor working, and also a lot of portion remains vacant there, so we can duplicate these slots there and we can use them. Although theoretically, when this microprocessor was designed, it was advised that you should have one section for code, one section of data. But now, people often have an habit of making this two code segments or sometimes multiple other segments also. So ideally, it is recommended that you should use one segment, means one code segment, one extra segment, one data segment, one stack segment. But if it is required in programming, you can have multiple of them in your program. You only have to keep track of where one section begins and where one section ends, right? So 16-bit data bus is known to us, 20-bit address bus is also known to us. It has a 6-byte instruction queue. So this is one point which is necessary for us to understand, that the 6-byte instruction queue, it makes the working of execution unit and your bus interface unit independent of each other, and this phenomena is called as pipelining, and this is the secondary reason for making 8086 microprocessor perform better as compared to 8085, because the fetching of the instruction part is separate from execution of the instruction part. In 8085, first fetching happens, then decoding happens, then execution happens, then again fetching happens, decoding happens, and execution happens. Here what is happening is fetching is separate. It is happening depending upon the vacancy in this queue. If 2 bytes of this queue are vacant, fetching will happen irrespective of what is happening inside the execution unit. So the operation of these two units is independent. Since this microprocessor is separated into these two units, it is performing in a more efficient way. So this 6-byte instruction queue is very helpful in that. So its speed is high. Now you have got a 16-bit arithmetic logic unit, which is very obvious because it's a 16-bit microprocessor. So most of the instructions are designed to work on 16-bit data. And the primary reason is we have a 16-bit data bus. Other reasons for calling it a 16-bit microprocessor is that the ALU is of 16-bit and most of the instructions are also of 16-bit. So it has got segmented memory, segmented external memory, not memory. Memory is not present inside this 8086 microprocessor. It has to be externally interfaced. So this externally interfaced memory of 1 megabyte is segmented. It is divided into code section, code segment, data segment, stack segment, and extra segment, and their corresponding base addresses. We will come to know what base addresses are. So these base addresses are stored inside the microprocessor in the corresponding registers with the same name. This is CS, DS, SS, and ES. This is not X, this is ES. So code segment, data segment, extra segment, and stack segment are external to the microprocessor in the external memory, and the corresponding segment registers of 16 bits are inside the microprocessor. So here it also makes it clear that why these registers are of 16 bits, because I already told you that inside the memory the starting address of these different segments have to be such that the last hexadecimal digit should always be 0. That means only first 16 bits or the first 4 hexadecimal digits of addresses will vary. The last 4 bits are by default understood to be 0. So the base address means the starting address of this these segments, and it is of 16 bits only because last 4 bits are always assumed to be 0. So that is why these have a size of 16 bit only. So this makes it clear here itself, and we will discuss it when we will understand the address conversion logic in the subsequent lectures. So these individual segments are of 64 kilobyte each, and they are in the external memory, right? Now, there are these pointer registers. Instruction pointer, we have already known it is a replica of program counter there. Then you have stack pointer, you have base pointer, you have source index, you have destination index. Then there is a clock of 5 megahertz frequency with duty cycle of 33% in base variant. In 8086.1, we use a clock of 10 megahertz, and in 8086.2, we use a clock of 8 megahertz again, right? So this is a quick summary of this 8086 microprocessor. Let us now also discuss some important points of differences between 8085 and 8086. I will just brush up. So 8085 has got 16-bit address lines. So 8086 has got 20-bit address lines. So this is very clear to us. 8085, it has 256 input output devices. When we were studying 8085, we said that there are two ways for addressing. I mean, you could have IO mapped input output or memory mapped input output. So in IO mapped input output, we were only making the usage of the data bus, not the complete address bus. So the lower order address bus was considered as data bus, and it was duplicated there. So since it has its data bus size is 8 bits, so it can address 2 raised to the power of 8, that means 256 input output devices. However, by the same logic in 8086 microprocessor, since it has got an address bus of size, it has got a data bus of size 16 bits, so it can address 2 raised to the power of 16, that is 64 kilo input output devices. 64 kilo. 64 kilo does not mean kilogram. Kilo is just a suffix that you are using. So kilo means you have got 1024. So 64 kilo input output devices can be theoretically connected to it. We already know what is the operating frequency, 3 megahertz and 5 megahertz for 8085 and 8086 respectively. Then one important point is this 8086 IC can operate in maximum and minimum mode. However, 8085 IC can operate in only single mode, and that's not given any name. So 8086, when it is alone working as a processor in a big network, it will be operating as in minimum mode. However, if there are multiple processors, then it will be operating in maximum mode operation, right? So we have got segmented memory in 8086, and in 8085 we do not have segmented memory, right? Now program status word, as we saw in 8085, it was a combination of accumulator and the flag bits, right? So in 8085, program status word meant a combination of accumulator as the higher byte and flag register as the lower byte. However, in 8086, the program status word will simply mean the flag register only. So flag register and program status word are the same. You do not have to club accumulator with them, right? So in if you see the flag structure of this, let me again show you that slide. Let me just bring that slide of flag register for you. So if you see the flag register of this, here there are three flags, that is direction, trap and interrupt. Direction, trap and interrupt. So these three flags are also called as control flags. Direction flag, interrupt flag and trap flag. These are called as your control flags. However, in this 8085, these control flags are not available. So these control flags are available to the programmer directly through various commands for programming, and we will see that how that works, right? Pipelining is obviously available in 8086 but not available in 8085. So these are some points of differences to begin with 8086. And if you look at the architecture of 8086 again, you are already familiar with this. The only point of difference was the bifurcation of this into bus interface unit and execution unit. And also, there were certain new components which were introduced, like these segment registers, which are used to keep the address of various sections of the externally interfaced memory. Then there is this instruction queue of 6 bytes. So we also know that this is also different. This adder is additionally placed here for address generation logic, which we are going to study soon. Then this flag register is of 16 bits, which contains some additional 8 bits, which represents different other flags also. And this flag register is called as program status word only. So I guess this is a fairly good introduction to the architecture of this 8086 microprocessor. In the next lecture, we are again going to see the pin diagram for that. And pin diagram is a way by which we can know that how the externally interfaced world it interacts with the microprocessor, and what signals are generated at what time. So that's what we are going to see in the next lecture. And this is it for today's lecture, I guess. I will see you in the next video. Thank you very much for watching this.